All right, recording is rolling. So welcome to Monday, back from spring break. Got a lot of new materials together for you guys at the break. Today I've just got a thermodynamics PowerPoint lined up for you guys. I also gave you guys this page just now. Who does not have this page? Oh, okay. Okay. All right. So I think everybody's got one then. So one side says chapter 12 thermodynamics. The other side says chapter 13, bunch of topics including materials. So we're gonna take next couple weeks to do these topics. So here's how this is working. Today, I'll tell you guys the principles of thermodynamics, whatever I can fit in this class period, and then next couple days we'll solve some of those problems together, and then we'll do the same thing for some related materials, materials engineering, that type of stuff. Right? So probably take us a couple of weeks. What I'm thinking. Right, so here we ultraviolet. Flip the screen over. Let's see, present screen 2, PowerPoint. Run it. All right, and we are rolling. So thermodynamics. And so let's start with temperature scales. Why not? Ways to measure temperature. So these are the three main systems that are used. All right, so going to go right to left here. So start with Fahrenheit, the one on the right. Now, what is temperature? What are we measuring? You guys might remember going way back to August. I told you guys there were like these 7 fundamental things that you can measure in the universe. So for example, there was mass in kilograms, displacement in meters, time in seconds. And then throughout the year, we've been mixing matching those and creating composite units. For example, force, newtons, that breaks down to kilogram meter per second squared, blah, 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 right? And temperature was one of these like standalone fundamental things that you can measure. But there is a kinetic energy theory of temperature, which is that, well, the warmer something is, of course, you measure a temperature, say with a thermometer, right? The more temperature something has, the faster on average its molecules are moving. So this room right now, there's a temperature in this room. And if you looked at the motion of each, say like nitrogen and oxygen molecule that's floating around in this room, well, some are going a little slower, some going a little faster, but you could make it like a bell curve distribution of their speeds, and there would be like a median speed that would correspond to like some temperature in this room. All right, so the Fahrenheit system, this thermometer on the right, a lot of times we still use this in the States to measure weather. Got 32 degrees is the freezing point of water, 212 degrees is the boiling point of water. When the first systems came around, there is a whole story of where those numbers came from. I forget what it is. It's weird. Anyway, but then along comes the metric system where everything was standardized to like base 10 and factors of 10. And I said, well, hey, it would like make a lot more logical sense. Also playing off the properties of water. If we just set 0 to the freezing point of water and 100 to the boiling point of water, right? So there's your Celsius system. Now, a couple of tidbits on that. One is that the guy that actually came up with the system, Celsius, he actually proposed to have 0 as the boiling point and 100 as the freezing point of water. It was like after he died, everyone's like, we're not gonna do that. It doesn't make sense. So we got another thing is that 100 degrees Celsius as the boiling point of water is really only true at 1 Earth atmosphere. So if you like go up in the mountains, that's actually water does not boil at 100 degrees Celsius up in the mountains. I want you guys to think what that would be, to do some critical thinking, because I'll ask you guys later. I'll see show hands what you guys think. Does water boil closer to 97 degrees Celsius or 103 degrees Celsius up in Denver, Colorado? Right, it's going to be one of those. But yeah, if we run into some alien civilization one day and they're like, hey, what temperature system are you using? And they see Celsius, like just makes complete logical sense, but they was like, ooh, I don't see anything special about 100 degrees Celsius at all, because on our planet, of course, water doesn't boil it, right? Okay, so it's all fine and good, right? Now, much later on in this presentation, one of the things I'll tell you guys about is something called ideal gas law, or there are going to be certain equations that involve temperature, right? Certain temperature changes, right? And if you want to do something like double the temperature to have something proportional to a temperature change, well, how about this? What if you go from 10 degrees Celsius here to 20 degrees Celsius here, from 10 to 20 degrees? Is that a doubling of temperature? What are you really doubling? Well, you're not really doubling anything except for the number that happens to be on the Celsius scale. What you really want is an absolute scale, and Celsius is a relative scale, just like Fahrenheit is a relative scale, right? Celsius and Fahrenheit can both go into negative territory, but it's not really negative of anything. It's not like if you're at negative 10 degrees, you like owe somebody 10 degrees, like, oh, I'm in debt 10 degrees. No, it's just a relative thing. So you need an absolute scale, and that's what Kelvin is for. So Kelvin was developed, right? So stick at Celsius for one more point. Celsius can go down to negative 273.15 degrees. There's no such thing in the universe as negative 274 degrees Celsius, because once you hit negative 273.15 degrees Celsius, you are at absolute zero. The motion of the molecules has come to a stop. In fact, it's so cold that it's not even a solid anymore. It actually transforms into a new state of matter called a Bose-Einstein condensate, because the atoms just like collapse in on itself, turn into like a weird quantum state. But that absolute zero would be actually a good point to start from on an absolute scale. So that's what we got for Kelvin. Absolute zero is zero, and Kelvin has no negative numbers to it. Right? Now, Kelvin was scaled the same as Celsius. So a change in 1 degree Celsius is the same thing as a change in 1 Kelvin. And you can see that here. See how from 0 to 100 degrees Celsius, so it's a change of 100 degrees. That's from 273 Kelvin to 373 Kelvin. It's also a change of 100 units, isn't it? Right. So it's scaled the same, but it just starts at a different place. Right. Now, if you want to convert Celsius to Fahrenheit, that's a 9/5 ratio, and then there's another plus factor. And anyway. All right, let's look at laws of thermodynamics. You guys remember how laws of motion, there's just a handful of very fundamental laws that lead to all different complex outcomes. So a very similar story here. Got a very few number of fundamental laws, and then all kinds of fun outcomes from here. So the zeroth law, when it's so fundamental, it's just called the zeroth. Two systems in equilibrium with a third system are in thermal equilibrium with each other. Okay, what does that mean? Well, thermal equilibrium means that they would have the same temperature as each other. So if you put thermometer on one and thermometer on the other, this one says 27 degrees Celsius. This one says 27 degrees Celsius. Put those two objects in contact with each other, there's going to be no heat exchange. Heat is a transfer of thermal energy. Maybe I should spell out the definitions of these things in this PowerPoint too, but that's what heat is. Heat is a transfer of thermal energy. If something feels hot, that's probably because it's transferring thermal energy to you. If you were holding onto an ice cube and that ice cube feels cold, well, there's no such thing as cold as a substance in physics. There's just the absence of heat. So if something feels cold, it's because there's thermal energy going from you into that ice cube, like melting the ice cube, something like that. Okay, so but if things have the same temperature as each other, then they are in equilibrium with each other, and there's going to be no heat transfer. Right? All right, first law of thermodynamics is one that you already know, and that's that energy is conserved, conservation of energy. So energy can change forms. Our last semester examples were like kinetic to potential energy, something like that. You can't create some number of joules and you can't destroy some number of joules. Now, what you don't have yet, but you're going to get really soon, is an equation to represent thermal energy, right? Because, you know, kinetic energy, 1/2 mv squared, potential energy, mgh, right? You know those, right? Energy stored in a spring, 1/2 k squared. But how can you quantify, say, something that could be converted into a temperature? I might do something like Q is like MC delta T or something like that, but that's coming up pretty soon. Okay, so it's pretty easy to grasp onto so far. All right, the second law, oh boy, here's where things take off and become really abstract real fast. So you guys see that word entropy? Yeah, this is a real abstract concept. I've got some slides coming up to do my best to explain this idea, but what does it say? Entropy of an isolated system always increases. You might say the energy of a closed system always increases, the energy of the universe always increases. And this is a law that's a statistical law. And it explains all kinds of things that you wouldn't normally think it does, like why does heat flow only from hot to cold, but not cold to hot? Why do systems move in one direction? How does this somehow help indicate the arrow of time? Why does time even move forward? What does it mean for time to move forward? Or how could you measure things to indicate that time is moving specifically in one direction? And the second law of thermo to say that entropy is increasing is an indication of that. And then the third law of thermodynamics, entropy of a system approaches a constant as the temperature approaches absolute zero. I've seen different wordings of this. So basically, I interpret this myself as like a baseline place to like zero entropy state. Right? So maybe if you take all the energy out of a system, take its temperature down to absolute zero, like 0 Kelvin. I've seen another definition that says like this specifically applies to a crystal structure because a crystal would be like an ordered form and which indicate low entropy. So I don't know. Anyway, there you go. There's your laws of thermodynamics. So we got next here. All right, this slide. Now this is a rehash of the zeroth law, or sorry, zeroth law. But I'm going to come back to this slide later for some other reasons. Right, so let's say you put a hot sink next to a cold sink. I got 100 degrees Celsius water next to 0 degrees Celsius water. Right. Walk away from that, come back a few hours later, you might expect something like this to happen. They reach eventually a state of equilibrium where they're both 50 degrees Celsius, if it's a closed system and all the energy stays in the system, all right? Now, the rate that this happens is called Newton's law of cooling. That transfer happens really fast during the first few minutes and then like slower and slower as time goes on, and then it reaches equilibrium. And then at that point, the heat transfer stops, right? Now, I'm going to come back to the slide later because you would totally expect to go from the left picture to the right picture, but what you would never expect to see is to go from the right picture to the left picture. If you had a lukewarm tank next to a lukewarm tank, walk away, come back a few hours later, you'd never expect all the heat energy to go to the left side and now one's like ready to boil and the other one's like ready to freeze. But that would be weird. Now, why is that though? That's related to the second law of thermo, which is that weird one with the entropy, right? The entropy. Right? Oh, speaking of entropy, here we go. What is entropy? Well, I've got a couple of perspectives on this. Got a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work, often interpreted as the degree of disorder or randomness in the system. Right. So let me start with the second thing they said and then go back to the first thing it said. Right. So degree of disorder or randomness in a system. So low entropy is like a highly ordered state. High entropy is like a lot of chaos and low order. Classic example I like to use is a sandcastle. So a sandcastle is a very highly ordered state for the sand to be in. Right? There's only like one way the sand can be ordered to make that particular sandcastle. Right? It took some effort to get it like that. If you created that sandcastle and walked away and came back a couple of days later, you would totally expect for that to have turned into a random pile of sand. Okay? And that random pile of sand, maybe there are many, many, many ways that you could create that random pile of sand. It's a less ordered form for the sand to be in. What you would never expect to happen, though, is if you create a random pile of sand to walk away from that and come back a couple of days later and just spontaneously turns into a sandcastle. Like that's never going to happen. That's never going to happen because of statistics. Right? It's just statistically, there's only very small ways for the left picture to happen, but many, many, many ways for the right picture to happen. And so it'll tend to happen that way. And the same thing happens with heat energy. So let me go back to the first part of the statement. Something about the unavailability of a system's thermal energy for conversion into mechanical work. So say you take a gallon of gasoline and put that in your car tank and then make your car run. Well, what are the energy conversions going on during that process? So first law of thermo, of course, says that the energy is conserved. So you're not creating or destroying energy, right? You're transferring from, well, it started as chemical energy and the chemical bonds in that gasoline, right? There's some like organic chemical bonds, right? Like octane and blah, right? And then it's going to transfer to mechanical work. So there's your kinetic energy, like making the car go, right? Or maybe potential energy if you're like going up a hill, something, right? But some of that energy gets transferred into less quality forms of less quality, right? So if you fuel the engine after you run your car, the engine's really hot, right? That heat energy is less quality than the motion of the car, the mechanical work, and the original chemical bonds in the gasoline. Or how about the car like fighting air drag as you're like driving along the road? It's fighting a bunch of air drag. So a lot of energy goes into that, right? Things like that. That's energy that you can't really recapture and keep rerunning the car with. I mean, if you could somehow recapture that energy, oh, I've got the same number of joules that I started with because energy is conserved in the universe. I've got the same number of joules. Then it would be nice to say like, hey, maybe I could create some form of a perpetual motion machine where I could just keep rerunning that energy back into the car and making the car go. But you can't. Why can't you? Because the energy is going from high quality to low quality, and you can't recapture the low quality energy and make the car run for it, right? Right. So there's some different perspectives on entropy, which is of course fundamentally involved in the second law of thermodynamics. Let's read this real fast. That states that the total entropy of, say, a closed system or the universe, which is the thermal energy per unit temperature, that is unavailable for doing useful work can never decrease, right? Or you could just say it's always increasing, right? In general, right? Staying the same or increasing. So I told you guys the example of you would expect warm container water to like the hot sink to transfer thermal energy to the cold sink, but not the reverse. Or second law of thermo is also used to explain like the picture on the left here. Like if you blow up a balloon and let it go, then the air is going to flow out of the balloon, but you would never expect the balloon to spontaneously fill itself, right? It would take effort to do that. Okay? And entropy has equations, like weirdly enough, it has equations, you can quantify, it has units, the whole deal. So here we got the first equation. The change in entropy, which would be an increase in entropy, right? If you're going forward in time, right? Is the heat exchange, that's what delta Q is. So this week, capital Q stands for heat energy. Delta Q is like a heat exchange. I see that delta Q right there, like heat exchange, divided by the temperature that this process is happening at. And this would have units of joules per Kelvin. Wouldn't that be energy per temperature, right? Joules per Kelvin. So that's actually how you can quantify entropy. It'd be some number of joules per Kelvin. And the second equation is what the second law of thermo says that the rate change of entropy with respect to time, right? That's a calculus term, but that's what it says, is greater than 0. So as time ticks along, there's always going to be more and more and more entropy, or the same, right? Greater than or equal to. Right? It can never decrease. Right? So that can never decrease. That's what this quantum equation says. Okay, for that. Right. Tell you what though, I have seen that this is one of those laws of this is one of those laws of nature that's sort of begging to be broken, because it's really a statistical law. It's just you watch so many systems happen, and it's like, oh, you can always like stir milk into coffee, but you can never unstir the milk out of the coffee. That would just be crazy, right? It's another second law, the thermo example, right? But if you get on to like small enough scale, if you're down to like 10 molecules, and you're watching those 10 molecules interact with each other, every once in a while, actually this law is broken. And sometimes you get like a more highly ordered form of those 10 molecules, but we're only talking about like 10 molecules at a time. So is it possible, is it foreseeable that, I don't know, maybe like tens of thousands of years in the future that, humans or whatever comes after us is able to figure out how to break this law together and create, sort of like second law perpetual motion machines? I mean, maybe that's, I don't know, maybe within the realm of possibility. That's what's fun to think about. Okay. Now, let's look at heat transfer, different kinds of heat transfer. There's 3 main types, and they're all nicely encapsulated in this picture. So you have a pot of boiling water, and maybe have a metal handle to this pot, and touch that metal handle. Well, of course, it's going to feel hot because, and that's called conduction. So conduction is the direct contact between 2 surfaces, right? 2 surfaces directly contact each other, and there's going to be a direct transfer of heat energy. Radiation, switch over to radiation here. You guys know about that one already. This is like electromagnetism. Radiation is the one that can go through the vacuum of space. That's how electromagnetic energy gets from the sun to the earth, right? Through radiation, vacuum of space, right? And the other one here is convection, right? So we've got radiation, conduction, and convection. And convection is like bulk movement of fluids. So it could be steam, it could be water. In this case, you have hot water in the bottom and cold in the top. Well, that wants to equalize, so it starts to churn and starts to mix. It could be like a convection, right? Since we're talking about convection, side thought here, I want to talk about ocean currents. Right? So here are some ocean currents that have been stable for thousands, if not millions of years. These ocean currents have been stable like this. So what are the drivers of these currents? Okay, well, part of it's convection. Right? There's a few reasons. I'm going to go through the few reasons that sets up these currents this way. And so one is, say, temperature convection. So if you have warm water near the equator and cold near the poles, then okay, well, that wants to equalize. That starts to prompt some kind of motion. Right? So you get some kind of motion from that. There's also salinity differences, right? So how salty is the water? I mean, imagine if you're near the equator, there's probably a lot more evaporation of that water. So that leaves behind saltier water, right? And then, okay, so that wants to equalize. That also prompts these ocean currents. Wind is another factor. Last class, Caden had just brought up Coriolis effect to look at the specific like northern hemisphere, southern hemisphere motion. You guys remember Coriolis effect? If you change latitudes, in the northern hemisphere, you tend to drift off to the right, and southern hemisphere, you tend to drift off to the left. You guys say, ooh, I see an Atlantic Ocean clockwise here, Pacific Ocean clockwise, but in the southern hemisphere, it's the opposite. You guys see counterclockwise. You guys see that? Ooh, Coriolis effect going on, right? All right, so there you go. There's a bunch of drivers of these ocean currents. Now, I've heard the speculation nobody quite knows, but who knows? Just an idea out there. Actually, wait, gotta set this up before I say that. Look at the latitudes of some of these countries around the world. Like, look at the latitude of England compared to, say, like over in North America. Draw a line straight west to North America. Oh boy, that's like up here in like northern Canada, like Canadian Shield. Wait, how is it? And most Canadians actually live like south of this line right here. Like you guys know this long border with Canada. If you just draw straight east, most Canadians actually live like down in this part, like more than half. So almost nobody lives like north of it. That'd be crazy. But if you're in England, which has kind of a temperate climate, well, you do. Right. So how can England have a temperate climate and that be nothing like tundra? Well, it's because of the Gulf Stream that runs right by Florida, right by us. Right? Carries a bunch of warm water and warm air up to Northern Europe. Right. Okay, now back to, I was gonna say, since the Earth is undergoing a lot of climate change, one thing that we're keeping our eyes on is the ice sheets over Antarctica and over Greenland. And of course, there's some tipping point temperature called 0 degrees, where that changes from a solid to a liquid. And would it be possible if you dumped lots and lots and lots of fresh water into the oceans that it could somehow disrupt these currents and therefore possibly that Gulf Stream wouldn't carry all that warm air and water up to Northern Europe? Maybe, but stay tuned. You might find out one day. Let's look at phase changes. So you guys know solid, liquid, gas. But what's the story to go from one to the other? That new page that you guys have in front of you has, of course, a bunch of problems on it. We're going to solve those in the coming days. And some of the problems deal with phase changes. So say you take I'll tell you guys a story now, build a really good mental model in your head today about how this works. And then when we go solve this, okay, I see how that works with this model, right? Right. So say you take an ice cube out of the freezer. It's like -10 degrees Celsius, right? -10 degrees Celsius. Right? Then throw that on a pan on the stove. It's going to start to heat it up. You guys see going to the right on this graph, we're increasing heat energy. Okay, so we're transferring energy into the ice cube. That's going left to right on this graph. And going up on the graph is increasing temperature. So, okay, we've got -10 degrees Celsius ice cube. Now it's -5 degrees, -3, -2, -1. Then it hits 0 degrees Celsius, and now it starts to undergo a phase change. Undergoes this melting process. But something funny happens. You guys notice that the temperature is actually stuck at 0 degrees Celsius during that phase change? Right? Well, I'm assuming for water, right? If we're talking about water for this graph. Now, maybe every chemical has a graph that looks kind of like this, but water is a really good example because you commonly see these different phases for water. And so it's stuck at 0 degrees Celsius as this thing is melting. The left end of this particular leg of this journey is 100% ice. The right end is 100% liquid water. And in the middle, it's a mixture of ice water. So if you have just like a cup of ice water, just like sitting on the table, and you throw in a thermometer into that ice water, it will read 0 degrees Celsius. You can try it. It'll do that. Now, if it's like half ice, half water, then at this point, if it's like the last dregs of ice are melting, it's probably like closer to the right end of this, but it's all stuck at 0 degrees Celsius. Now, once it turns completely into liquid, now the temperature is allowed to rise again. And then you got 50 degrees Celsius, 60, 70, 80, 90 degrees Celsius, 95, and then boom, 100 degrees Celsius. Now it starts to undergo a phase change again. It starts to boil, right? And then same funny thing happens as before, is that the temperature is stuck at this, well, in this case, it would be 100 degrees Celsius if you're talking about water at 1 atmosphere, say down here at sea level, right? Stuck at 100 degrees Celsius. What if you do this though? What if the water starts to boil? You say, you know what, I want this water to be really hot. And you, let's say it's like a gas stove and you turn up that flame a lot higher. And now the pot that the water's in, even that metal starts to get hotter, right? Does the water itself get hotter as it's boiling? No, it's stuck. It's stuck at 100 degrees Celsius. Now it might boil faster, right? This process might speed up. We're going to the right faster on this graph, but it's stuck at 100 degrees Celsius. Sometimes boiling is called a cooling process. not because it's cooling off anything around it, but because the water itself, that mass of water that is undergoing boiling, well, think about the transfer of energy, heat energy going into and out of it, right? You got the flame beneath it that's pumping heat energy into that system, right? Into the water, right? And then the boiling is carrying energy out of it. That's why it's stuck at 100 degrees Celsius. So that boiled water take off, right? What if you had a pressure cooker? If you like throw a lid on that pot and you have it sealed, in that case, can the temperature go above 100 degrees Celsius? How many guys say yes if you have a pressure cooker? Pressure cooker temperature can go over 100 degrees Celsius. Yeah, right. Because remember, this is only for one set pressure. You change the pressure, it goes out the window. You go over 100 degrees Celsius for like that. Okay. Oh, let's go back to Denver, Colorado, because I actually asked this question before I set this up. So how many guys have ever been up in the mountains, running around where the air is really thin, up in the mountains? Right. Yeah. If you guys never had the opportunity, then at some point try that. Go up to the mountains, try to run around. You'll get winded really fast because the air is really thin. A lot of athletes like to practice up there because then they come back down to sea level and it's like, oh, I've got all this oxygen. Right? So where the air is really thin, do you think water boils closer to 97 degrees Celsius or closer to 1 or 3 degrees Celsius? How many guys say up in Denver, Colorado, water boils closer to 97 degrees Celsius? 97. Yeah, there's my winners right there. Closer to 97 degrees Celsius, because the air pressure above actually is one thing that helps prevent water from boiling. Okay. If you remove that pressure, water will boil more quickly. So it's easier to get water to boil up in the mountains. On the flip side, of course, you can't get the water as hot. So if you're like, I need a recipe that needs the water to get to 100 degrees Celsius, well, it's not going to happen, say up in the mountains. Okay? Actually, I don't know if I was quite ready for this, but why not? I'll show you guys reduced pressure boiling. Here we go. Reduced pressure boiling. No. Hold on. I want to go back to, I'm not ready for that yet. Not ready for that yet. That's coming up though. Right, let's go back to here. Right. Sorry guys, getting a little ahead of myself. Let me go to tell you guys some of the mathematics of this graph that we're going to eventually apply. Right, so delta Q, that's like an exchange of heat energy. That's like going to the right on this graph. That'd be delta Q, right? Increase the heat energy, right? Okay, what are these other bits? So M is like the mass that we're trying to heat up. Let me skip over to this delta T. Delta T is like a change in temperature, right? So it's like going up on this graph. Do you guys see this looks kind of like y equals mx plus b, sort of, except the axes are flipped, right? Right, so got going to the right on the graph is delta Q, going up on the graph is delta T, right? Okay, so M is the mass that we're trying to heat up. What is C? C is specific heat capacity. Here are specific heat capacities for different materials. You guys see water down here in the bottom right? Water, 4,186 joules per kilogram Kelvin. Do you guys see that that's the largest number on this entire table? What that means is that water has an enormously high heat capacity. That means it's really, really, really hard to change the temperature of the water. It's really hard to heat up water, really hard to cool down water also. But you guys probably already know that because you put water in a pot, throw that on the stove, the pot itself heats up real fast. The pot's made out of metal. Some of these metals have much lower heat capacities, right? But water takes a long time for the water to boil. And once it is hot, it takes a long, long time for it to cool down too, right? Graphically, because remember this graph's kind of like inverted backward, it's like the reciprocal of the slope of this line. So this liquid leg of this graph, water compared to other materials has a very shallow slope. It takes lots and lots and lots of heat energy. You have to go to the right on this graph a long, long, long way just to heat it up, change the temperature a little bit, right? So that's what so that's C, that's embedded in that C. So let's go over this again. Delta Q, the heat energy transfer, equal to M, the mass that's being warmed up, right? Or cooled down for that matter, right? C is the specific heat capacity, that's these numbers, and delta T is the temperature change, right? But you might look at this, the flat legs of the graph during those phase transitions, the melting, freezing, or vaporization and condensing, and say, well, there's no temperature change during those parts. So if I had an equation for those, it might have something to do with like the lengths of those, but not really the temperature change because there's no temperature change. Yes, that? Right. That's what that bottom equation is for. You can have a heat exchange. That's what delta Q is. You can go, you can go right and left on this graph, right? For some mass of something that you're trying to heat up or cool down. Delta H is referred to as either the heat of fusion or the heat of vaporization, depending on whether you're, well, melting, freezing, or boiling, condensing, right? Let's get that. And let's check out water. So water has, for latent heat of fusion, 334 kilojoules per kilogram, and latent heat of vaporization, 2000 and something kilojoules per kilogram. And so what that means is that for water on this graph, this leg of the graph is like 300 something units long, and this leg is like 2000 something units long. Right? Guess that? Okay. Right, and we'll run the math on that next few days. Okay. All right, now let's expand our view and go two-dimensional, because this whole graph we've been looking at is at some particular pressure, maybe like 1 atmosphere of pressure, 101,000 pascals, something like that. Right? Well, let's go into two dimensions. Say, well, treat pressure also as a variable, right? You guys see that? Because on this graph, going across the top, I got temperature. You guys see temperature increases linearly, 50 Kelvin, 100 Kelvin. We got 200 Kelvin, 300 Kelvin, 400 Kelvin, 500 Kelvin. Okay, so it's increasing linearly. You guys see that? Right? Do you guys see two vertical red lines? One is at 273 Kelvin and the other is at 373 Kelvin. And I know that because those correspond to, down at the bottom, 0 degrees Celsius and 100 degrees Celsius, probably a couple important numbers, right? But what about what's happening vertically on this graph? Pressure. Okay, so pressure, you guys know, is measured in pascals. Here's 1 Pascal, 10 pascals, 100 pascals, 1,000 pascals, 10,000, 100,000, 1,000,000. That's not scaled linearly. That's scaled how? Yeah, exponentially. You could also call that logarithmically. So if you said exponentially or logarithmically, like two sides of the same coin. Yeah. So by a factor of 10, which if it was not that, this graph would be really an eyesore to look at. But this fits very nicely on the screen, right? And there's a very important horizontal red line that goes across. And it's at 101,300 pascals. And I know it's at that number because that is 1 atmosphere. You guys see 1 atmosphere right there? Right. So here is about where we are in this room. We're at 1 atmosphere of pressure and about 20 degrees Celsius. That's about room temperature, right? Somewhere there, right? A very cold winter day in Florida is probably right here. Very hot summer day in Florida, probably right here. Here's kind of the space that our brains are able to make sense of. That's like all our life space, right? How do you boil water? Throw it on a stove and heat it up. But there's another way to boil water. Do you guys see what that is? To drop straight down to decrease the pressure. And that whole story I was saying with like boiling water in Denver, well, that would be probably right about, I'm going to exaggerate a little bit, probably about here-ish, right? To the bottom left of the boiling point at sea level. You guys see that? Okay, yeah. So now I'm about ready to play that video that I'd almost pulled up and played prematurely, where we're going to boil water by going straight down and across this line. You guys see that? You guys see that? Right. You guys ready for this? Ready for this black magic? Let's see, where are you? Here you are. All right, so, hey. Oh, it's a really long intro. Okay, so beaker, water, throw it in a tank, gonna vacuum out all the water. So really low pressure and then low pressure, boiling. Now let's see, how many guys are following here? If you touch that boiling water, that would feel very what? Very hot or very cold? Why is that water boiling again? Not because of increased temperature, because of reduced pressure. Yeah, it's called reduced pressure boiling. Right? It would feel very cold. In fact, it feels so cold. Do you guys see a layer of ice? Whoa, where'd that ice come from? That ice. Why is there ice in there now? Remember I just told you guys a few minutes ago that boiling is a cooling process. And when I say cooling process, I mean that it's taking energy, thermal energy out of the water and it's dumping it into the wider atmosphere, right? Isn't that what's happening? That's what just happened. Yeah, so boiled that water, not because of increased temperature, but because of decreased pressure, but the boiling itself took thermal energy from the mass of water, dumped it out into the atmosphere, and there you go, you're left with a block of ice. Ooh, spooky. All right, well, we're done with that one anyway. All right, reduce pressure boiling. Okay, so that's going from here to straight down. That's what you guys just saw. Okay, can you go straight from a solid to a vapor? Is that possible? Yeah, and there's a word for that. It's called sublimation. That's the scientific word, sublimation. I bet. Yeah, dry ice, right? Right. Which is actually carbon dioxide, right? I should have asked you. You guys would have said that anyway, right? Dry ice is carbon dioxide, right? That's something that undergoes sublimation, right? That's why it's dry, right? There's nothing wet about it. It just goes straight from solid to a vapor. Now, even though this graph is specifically for water, all the numbers line up for water. You can do similar looking graphs for other substances too, including carbon dioxide. Okay? Look at this point right here, this triple point. Can you have all three phases at the same place, same time? Solid, liquid, gas? Huh, I wonder what that would look like. Let's look at the triple point. Would you guys like to see some boiling snow? I would like to see some boiling snow. I should tell you guys, this isn't actually water. It's some other chemical, but same principle, I guess. Something in my brain says it's like cyclohexane or something. I don't know. It's a long time ago. Got the wrong word in the file. Ooh, see some. Ooh, that snow starting to boil. Hey, look at that. Boiling snow. Triple point. Now it looks like it's kind of hard for them to hit that triple point because you have to hit exact temperature and pressure. It's probably not very stable. Probably kind of like trying to balance a baseball on the tip of a pencil, right? But there you go. The triple point. That is cool. All right. Ideal gas law. All right. How many guys? Let me see, show of hands. How many guys learned this in chemistry? Ideal gas law. Learned this in chemistry. Okay, couple of guys. Yeah, that's what I've been seeing all day. I've had like 2 or 3 students each class, and I guess there's like different chemistry teachers. All right, I'll teach you guys. Ideal gas law. So this relates pressure, volume, and temperature for like so massive gas, right? And this is actually a composite. Ideal gas law in big bold up here is actually a composite of 3 predecessor laws that led up to this. So let's go through this one by one. Gay-Lussac's law says pressure is directly proportional to temperature. Now this one, ignore the balloon for a moment and imagine a steel can. Can you guys imagine like a steel can and it's like full of water and you throw that on the stove and start to heat it up, which increases the temperature. Is that going to increase the pressure until maybe at some point the can explodes? That's Gay-Lussac's law. Jump down one. Charles's law, volume is directly proportional to temperature. Let's bring in this green balloon here. If you increase the temperature of that balloon, is that going to increase the volume for some given pressure? Yeah, in fact, it's a direct proportion. So if you double the temperature, that should double the volume for some particular gas, as long as it's an ideal gas. Okay. What about this? If you go from 5 degrees Celsius to 10 degrees Celsius, is that doubling the temperature? No, because you have to use what temperature scale? Kelvin, which would be an absolute scale. And in that case, you're only going from, what's that, about 280 to 285 Kelvin, something like that, right? So, okay, so it's a smidge increase, right? So you watch that balloon increase, but only by like a little percent, right? Something like that. And then Boyle's law says that for a constant temperature, pressure is inversely related to volume. Right. I mean, each one of these laws, we're assuming all else held constant, right? Also is controlled for. So let's take this balloon now and squeeze down on it. Can you imagine if there's a fly flying around inside the balloon and you're squeezing the balloon? If you're squeezing the balloon, aren't you decreasing its volume? If you're decreasing its volume, what's happening to the pressure inside? It's going up, right? That fly feels like, oh, there's a lot of pressure inside this balloon. Hey, inverse relationship. Now we put those 3 laws together and you get back to this ideal gas law. Pressure times volume equals number of moles of gas times some R, which is a constant, times the absolute temperature T. So T, remember, has to be an absolute temperature measured in Kelvin. And R, well, there are lots of different values for R. It's just a constant. It depends on what units you're working with. I gave you guys 2 commonly used examples for R down here. So there you go. Right, ideal gas law. We'll solve some problems with those. I got some videos that aren't playing, so I'll check those after school and fill you guys in on the details tomorrow. All right, let's look at what version of the, well, let's do this one. I'll tell you guys about refrigeration and air conditioning, which is the same technology. And well, this is labeled heat pump, but it's the same idea, right? So how do you create cold air, say like for your refrigerator or for air conditioning? Say in this room right now, it's colder than the outside world, but how is that possible? It seems kind of hard. It's kind of easy to just set a fire and warm things up, but really hard to cool things down. So how do you do it? Well, ideal gas law might give sort of a hint. So let me scroll back to that. I would really like to decrease this temperature, right? Really hard to do. Why is that really hard to do? Let me scroll way back in this presentation because the second law of thermo. Remember, if you have hot sink next to a cold sink, then you expect that to equalize. But what if you had just like a bunch of muggy hot water or air and temperature? Okay? How can you get that cold? I'd really like to have that cold. Well, it's not spontaneously going to happen. That would break the second law of thermo, but you can force it to happen. And you can force it by, let's take a page from ideal gas law. If you want to decrease the temperature, isn't that like decreasing the right side of this equation? And if you want that to happen, maybe you have to decrease the left side of this equation by decreasing one or both of pressure or volume. Or maybe if one decrease faster than the other, right, increase, then that would also decrease the temperature, right? Some version of that, right? That might be maybe something to do with this expansion valve, right? Because if the pressure decreases here, right? If you have like some refrigerant going around and the pressure decreases, that would decrease the temperature, wouldn't it? Now you got a bunch of really cold fluid, right? Or air, refrigerant, whatever you have, right? And now you can run air past that, and now that's how you can cool off a room. Now there's another half of the story though, which is of course when you compress this to complete the cycle, you're going to have something really hot on the other side, and you want to carry that off back into the wider atmosphere. Right. That brings me to this right here. How many of you guys have ever walked through an old part of a city? Maybe there's some high rises that were built before air conditioning became prevalent. You see all these air conditioning units hanging out the windows, right? Just like this photo. You guys ever seen something like this? Or maybe you have something like this at home. I bet everybody in here has an air conditioning unit at home. And if you do, if it's not hanging out your window, then I guarantee you that there is an outside condenser unit. There's some piece of the system that is outside, like an outside box, right? Now, why does that have to be? Why can't you just have an air conditioner and just park it in the middle of a room, right? Or let me ask you guys a very related question. How about this? You go home into today and you open up your refrigerator door and just leave the refrigerator running with the door wide open, and all that cold air is dumping out the front. What's that going to do to the temperature of your house if you let that go on all day? Is that going to cool down your house or heat up your house? How many of you guys think if you leave the fridge running all day with the door open, that's going to cool down your house? Nobody says that? Ooh, smart class. Who says it's going to heat up your house? Yeah, it's going to heat up your house. Oh, wow, class full of winners. Now, why would that be? Why is it that you open the fridge door and that heats up your house? Because that cold air dumping out the front, well, that's only half the story. Don't forget the other half of the story is that if you reach back behind the fridge, you'll feel a lot of really hot pipes, right? There's a lot of heat that's being dumped out the back, right? And in fact, if you mix those two back together, the hot heat compared to the cold, even though there's no such thing as cold, there's no substance that's cold, but you guys get the idea, right? If you combine the air all back together, it's actually going to be warmer than it started with because this process is energy intensive. That's why your refrigerator, your air conditioning has to be plugged into the wall because it's pulling energy off the grid so that you can run this process in the first place. That's why you need these air conditioning units to be hanging out the window because they're dumping all the hot part of that process out back into the wider atmosphere. So the cold part can be specifically dumped back into the room, okay? Or in the case of your fridge, back into inside the fridge. Okay? Right. All right, we're getting real close to, okay, we're good here. There are a few different thermodynamic cycles. I'm going to show you guys two of them today. Carnot cycle, this is one of the most efficient thermodynamic processes you can have. You guys see pressure versus volume, and do you guys see two different temperature curves? So these are called isotherms, iso meaning same, therm meaning temperature, so same temperature. Right. So I see a hot sink here, and I see a cold sink here. Okay, so Carnot heat engine, you can run on a temperature difference, right? You can turn this into mechanical work, right? We're going to come back to Bill Nye. We will just hang tight. Right. Another process I want you guys to see is something called the Rankine cycle. This is how most electricity is generated. How do you get electricity from coal or from nuclear? Well, it all goes through boiling water. You boil water, turns a turbine. It goes through this process, right? So I'm going to end today on Bill Nye showing you guys a Stirling engine. Okay, so hang tight here. Let's do Bill Nye and his Stirling engine.
Let's say this beaker full of very warm water is a source of heat.